Here's a little help with the speed of sound problems in case you need it. Starting out, I'd like to make sure you know your equations you're going to be using. So they're very simple. We're going to go back to the first equation we learned back in September. Velocity equals displacement over time, or you could just say speed equals distance over time. Then when you're working with air, you want to remember that the speed of sound changes based on the temperature. So you want to use this equation to equate temperature with the speed of sound through air. Okay, so your first problem you're going to have, you're at a soccer match and you see a lightning strike, and then later you hear the thunder. If you're interested to find out how far away the lightning strike was, we can use these formulas. So start by turning the temperature into a speed for the speed of sound. Then use it in your velocity formula to get the delta x. How far away was that lightning strike? All right, you measured the time, you know the temperature, you should be able to figure this out. When you get your answer, please convert it both into kilometers and into miles. Put your work on the next slide, make sure it's neat, make sure I can follow it. The next one, you're going to take an old video of Mr. McCarron hitting a drum. We know he was exactly 75 meters away from us, and using our video tools, we were able to figure out how much time it took the sound wave to reach us. So this time you're going to work backwards and try and find the temperature on that day. So start with your velocity equation. Make sure you convert your time into regular seconds. Get your velocity, and then convert the velocity into a temperature based on the speed of sound in air equation. Put your neat work on the next slide. This next one, we're not sending the sound through air, we're sending it through the human body. So we have a ultrasound wave, and we're sending it in to study the heart. And we're going to have it travel a distance of 37 centimeters one way. So you're going to have to make sure that you double that to get the total distance. Use the total time to get the average speed of that wave. You should get a number that is much higher than the speed of sound in air. Remember, this is microseconds, and make sure you convert them into normal seconds. Put your work on the next slide. Finally, you have one where you're going to be working on your own. You'll each get a unique problem. And here's the scenario. You're in a field watching fireworks on the 4th of July. You know where the fireworks are being shot from, and you know where you're standing. We can use Google Maps or Apple Maps to figure out how far we are from the firework launch site based on the locations of those two spots. We're then going to fire the firework up. It's going to explode, and you're going to time it just like the lightning strike. You're going to see how much time it takes the sound wave to reach you after the explosion. You'll have the temperature. Convert your temperature into a speed into a distance. That distance will be the hypotenuse of your triangle. You've already measured your horizontal distance using Google Maps or Apple Maps, and your job is to find the height at which the firework exploded. All right? So you each will have your own unique problem. I do not need to see your work if you get the problem right. If you get it wrong, please show me both your work and your certificate so I could see if I could figure out where you went wrong. You can just put your certificate right on the page with the link, since most of that area is available to you. Good luck, and if you have any questions, come see me, Durham McCulley 1.